Okay, do you want me to start or should I wait?
No, go ahead.
Okay, so welcome everybody. I was just talking to Nick the other day, trying to gauge the level of the class. And I decided, irrespectfully of some of you guys know some of the material that I'm going to start with, it's always good to do a review, a little bit of I'm going to put the chat window nearby so I can see questions. Kind of to give an overview of what are the basic ingredients. And then we're going to dive into more specifics. So I was asked to teach you guys about the structure of the heliosphere. So in two parts. So this first part, I'm going to introduce some of the basic elements. I'm sure most of you guys know that, but feel free to interrupt if you have questions in any moment. And then we are going to dive into more specifics of the heliosphere. The outline of what I kind of thought for part one, part two, first of all, discuss what do we mean by heliosphere? What are the main components when you're thinking to introduce a subject to what are the main active ingredients when you're trying to cook up a heliosphere? How do we measure these characteristics of the heliosphere? And then I'm going to go through some basic material that I like to cover both in my intro classes, but also in more advanced classes like this one, because like I said, I think it's important for us to be on the same level of what do we mean the ingredients needed for the heliosphere. Okay. So I'm going to go through the solar wind, the interplanetary magnetic field, and then we're going to talk a little bit about the behavior of the solar wind at large distances. It's quite different than the behavior of the solar wind near the sun. And then more towards the last piece of part one, I'm going to introduce observations of the termination shock, Heliosheath, and we are going to talk about some puzzles of what we don't know about the heliosphere and what we're discovering recently. And again, feel free to interrupt at any moment. Okay, so first of all, what is a heliosphere? What do we mean by heliosphere? So we like to show this slide to introduce to the broader viewer that, you know, in a very broader way, heliosphere, the concept of heliosphere in a broader concept is equivalent to astrospheres for stars. And when you look up in the sky, you see stars. They seem to see just a point that is luminous, but they are not just a point that is luminous, and they're not, as we like to say, naked. They're surrounded by a cocoon. Those cocoons are called astrospheres. And the reason we cannot see a lot of the cocoons is because the cocoons are made of the winds that come up from the stars. And a lot, especially for solar light stars, those winds are very rarefied. So those cocoons, think about like a gauze that envelop a star. It's very thin, very easy to miss. For very massive stars, you can see a cocoon like that. And sometimes you don't see the whole cocoon, you just see the effect of this cocoon of the medium that surround the star, the interstellar medium, and you can see the shock here. For some stars that are much more massive, you can see the cocoon extending in a long tail in the back. So in a bigger picture, we will say astrospheres. And again, I decided to put some slides at the beginning to introduce the questions that you might want to ask yourself. Why do we even care? Why do we even care to have a class about heliosphere, besides that you are all space physicists? In a bigger concept, astrospheres protect life. Astrospheres are the last shield. Therefore, you have the background that I have a group studying the astrospheres called Shield. This is a shield that protects us or any star from whatever lies beyond us in the interstellar medium. So for us, the sun, or for stars near us, they're all surrounded by, we detected them indirectly, they're all surrounded by astrospheres. So again, in a bigger picture, this search for life, that we're looking for other planets around stars, you have to realize that those planets are sitting well within those astrospheres. So whatever impinge on those planets is already filtered by those astrospheres. And one of the questions we are interested, it's an open question, it's not something that we have the answer for that yet, is why our heliosphere, or why our astrosphere is habitable. And we have life, of course. We are looking for life in other stellar systems. So there is a quest, in this quest of trying to find other life, we should ask ourselves which characteristics these astrospheres have that make life possible. They do filter a lot of stuff. One of the most important ingredients is galactic cosmic rays that I'm going to tell you next. But one key message I want you guys to take away from this class, whatever puzzles we have in the heliosphere, whatever questions we are debating, this is our chance to study up and close an astrosphere and try to understand the characteristics of an astrosphere. So far, our heliosphere is the only habitable astrosphere. Okay, so to put us in a interstellar medium context, this is the sun here on the right in yellow. We are within, we think, a G cloud. This G cloud is sitting in one of the spiral arms. And if you look at the size of our heliosphere, and I will talk about it later in this class, it's only recently in the last decade that we found out the size of our bubble. When I came into the field back in 2001, I started working in this field 20 years ago. We had no idea about the size of the heliosphere. Right now we know that the size of our heliosphere is 100 AU. It's actually 127 AU to be precise. We don't think we have a bow shock ahead of us, and I can talk about it later on, but we do have a slowdown of the interstellar mediums that come into contact with our bubble. Our solar system, you can imagine, ends in the Heliopause. This is where you have material that come from the sun. So particles from the sun are not longer present outside. As you all know, two magnetized plasmas, when come in contact, they cannot share particles easily, at least. So the particles from the sun disappear as long as you come out of our cocoon. But we do have other material that is related with the formation of the solar system, the Oort cloud, etc. But this is just, it's a nice diagram to bring home the size, the scales that we're talking. Okay, so you heard a lot about space weather, the sun 1 AU. Now we're talking about scales of 100 AU, and you can think that the nearest stars, Alpha Centauri, it's more than 10 to the 5 AU. Okay, so what is a heliosphere? Definition: this is a cocoon or a bubble that the solar wind carve in the interstellar medium. It's formed because the sun has a wind, and we move through the interstellar medium. So the same way that as a boat moves in a river, we form a shell of deflected material that come back away from the motion that is right here in the nose. And here are all the planets in this, more or less in one single plane, and you can see the three-dimensional structure of the heliosphere. This three-dimensional structure is being called into question. So I will talk about it more in the part 2. What do we think it is? Until now, we always thought it was a comet shape. So in this diagram, the idea was that you have a very narrow cocoon heliosphere here and a very long cocoon extending backward to thousands and thousands of a year. And a little bit more wider towards the north and the southern pole. This image here is being debated now within the community, and there are ideas that the tail, if this is a direction that we're moving through the interstellar medium, the tail has more or less the same size. So we live within almost a bubble. There's a model that my group put forward that is almost a croissant shape. There are some jets coming out. I will talk about it later. But those are being debated, the shape of our heliosphere. And just to maybe spark your curiosity, when you look at other astrospheres, and here I'm showing 3 examples, they come in very different shapes and flavors. So it is possible that our heliosphere also change its flavors depending on the conditions that we are affected, either by the interstellar medium or either by the sun. So I'll come back to it and we can open for discussion. One key aspect of the heliosphere that I mentioned, the heliosphere is a great shield. And now we know, because we have probes that I will talk in a bit, the Voyager's probe spacecraft that left the bubble, that the heliosphere shields 75% of cosmic rays. Now, cosmic rays, I think you're going to have a class by Georgia Coloni about galactic cosmic rays. They extend to decades of energy. They are thought to be produced by supernova remnants, and they can extend to a couple of decades in energy in GeV. The ones that are affected by our heliosphere are the low energy ones, the one of 1 GeV or below, okay? So the 1 GeV particles get shielded 75%. We almost block all GeVs. And you can see that in this plot of the intensity of the galactic cosmic rays. You can think about time or distance to the boundary, but you can see that the intensity vary with time. This variation is due to the solar cycle, and Joe is going to tell you all about that. But as soon as you come into the heliosheath, that is the last boundary of the heliosphere, I will define those boundaries in a minute, you have a spike in the intensity and even a larger spike just a couple of years before the Heliopause, and it's plateaued to an intensity once you leave the Heliopause. Now, the question is how much you need to shield to have life is an interesting one, because you do need galactic cosmic rays. They are a key of some of the chemical reactions that are important for creation of life, but you don't want too much of them. So it's interesting that our astrosphere has 75%, and this should be explored more. Okay, so let's talk about, this is the structure of the heliosphere, the general, what is it? And now we would like to, Nina, did you have a question or no? No. If somebody has a question, just raise your hand or just interrupt me. Now I'm going to go through how do we measure heliosphere, okay? It's hard for me a little bit to see the videos of all of you guys, so it's best for me or for you to put something in the chat if you have a question, or to just interrupt me directly. Okay, Nick said he's also monitoring. Yes, thank you, Nick.
I'm monitoring chat, that's all I was going to say.
Okay, great. But I had in classes that I gave, people just raise their hands and I call them, or Oh, they put something in the chat. I have a question. Okay, so how do we measure the characteristics of the heliosphere? Let me present you the components of the heliosphere before we talk about measurement. So here I made a laundry list of things that you should know, when you're talking about the heliosphere. So heliosphere is composed by solar wind. So let me point, oh my God, every time I move my mouse, this thing jump. Okay, here is the sun. The sun produces solar wind. And the solar wind is a supersonic solar wind. And it goes through a shock. This is the largest scale shock in the heliosphere called termination shock. It's around 100 AU. And if you remember, I said the heliosphere is 127 AU. You figure out that this distance between the termination shock to the edge of the heliosphere, that we call Heliopause, is much thinner. So this picture here is not to scale. This Heliopause should be closer like this. It's 27 AU. It's very thin, at least in the nose direction. The region between the termination shock and the Heliopause is called Heliosheath. And the Heliosheath is, you can think about, this is a plasma that is a solar wind that was shocked. So it's a subsonic plasma that is being diverted by this obstacle, the Heliopause, and going down the tail, okay? That plasma has a magnetic field. So it's a magnetized plasma, close to being ideal. So you can think it's ideal MHD. We will talk a little bit about what do we think about this plasma. But this is a magnetized plasma that has a solar magnetic field that you all know. You heard from Dana from Amitav about dynamo, etc. So the solar magnetic field. This solar magnetic field goes through and is modified. It's the same one, but we do call it interplanetary magnetic field. Yes, and the plasma, right. So there was a question that then I answered, where the solar wind particles, if they're not crossing the Heliopause, where do they go? They go down the tail. So it's a conservation of mass. They come from the sun and they're diverted down the tail where they merge with the interstellar medium, okay? Opa, my mouse is, went to the wrong direction. Here. So the other component that we know of is that the plasma outside the heliosphere has a magnetic field as well. We know it's magnetized. So there is a component called the interstellar magnetic field. We don't really know the direction of it. We know a whole lot about the solar magnetic field. We don't really know a lot about the interstellar magnetic field. We know a little bit, and I will tell you a little bit about it, but we are not sure either its magnitude or either its direction. Because we are not exactly sure its magnitude and direction, we are not sure if this plasma needs to go through a shock as well as it's come into contact with the Heliopause. So this is why in this diagram, we show a bow shock with an interrogation point, because we are not certain. We have strong indication recently that this field, its magnitude is strong enough that this material here is subalphenic and it doesn't have to go through shock. So the bow shock is not present. But in this diagram, the interrogation point, because this is somewhat of an uncertainty. Now, this interaction is interesting because there are other components, not just the regular plasma that you're used to, but there is also the galactic cosmic rays that I mentioned, that are much higher energy than the plasma. So you can think about just as test particles streaming along. And they have a really large gyro radio. The size, if you remember what gyro radio is, a radius of the particle goes through a magnetic field, It's entered into the heliosphere, but has some interesting shielding properties as we talked, so, how they enter. The other interesting component are the interstellar neutral. And by interstellar neutrals, we're talking mostly about hydrogen. There's some helium, but mostly it's just hydrogen. And interstellar and neutral particles are not attached to magnetic field, and they can stream unimpeded by those boundaries. So interstellar neutrals can come into the heliosphere freely. There is an interaction that I'm going to describe next that couple the interstellar neutrals with the ions. So they do have some, if you want to say, a drag or friction between them. So they don't come completely unimpeded, but their mean free path is pretty large. It's around 100 AU. Okay, now, when the interstellar neutrals enter, they can be ionized near the sun, and they become a new particle, a new ion that we call pickup ion. So let me describe this in the next slide. And why this is interesting is because the solar wind, and this is a key difference between people, of you guys that are studying ionosphere, magnetosphere, solar wind near the inner planets barely has any pickup ions. But as you go to larger and larger distance, the amount of pickup ions increase and the whole interactions start changing because pickup ions will carry a lot of energy. So we will talk about it next. There was a question by Florian. We see that this bow shock is rippled. Is the termination shock also rippled or it's smoother? That is an incredible good question, Florian. And feel free if you want to have more, elaborate more than what you wrote in the chat. But in these diagrams, both the heliopause and termination shock are drawn as smooth. We don't think they're smooth. And I will come back to it later, probably in just part 2, talking about some of the puzzles of the measurement that we see. And we attribute that to the fact that those boundaries are not smooth. And they're probably also rippled by turbulence and by MHD instabilities and other stuff. But we do think that all of them are rippled. So it's true that in this diagram it's a little confusing why the bow shock is rippled and not the other ones. Okay, so let's talk about the pickup ions. Again, this is another one to remind you of the quantities before we talk about the pickup ions. Sizes, now we know that the termination shock is not symmetric, north and south. I'll come back to it later. There is a difference of 10 AU between north and south. The Heliosheath I talked about, termination shock I talked about. Let's just put some quantities that the motion that we're moving through the interstellar medium is around. There is some debate on that, but 26 kilometers per second. The ions, we're pretty sure that this is a density, 0.06. The temperature is a little bit of a debate, but it's around 6,000 Kelvin. If you remember your ISM classes, this means that this is a warm ISM. It's not a cold part of the interstellar medium and not super hot. It's a warm ISM. And what is interesting that the neutral in the ISM is an order of magnitude higher than the ionized component. It's 0.18 particles per centimeter cube. So this is a partially ionized interstellar medium where most of the density is not in the ionized component, but in the neutral component. So this is an interesting in itself. The solar wind, we will talk more. It's very variable. As you know, you saw in the lab with make a fast and slow wind. So some variations. Okay, so let's talk about pickup ions. Pickup ions are formed when the interstellar neutrals, and now we said it's an order of magnitude higher than the ionized component, come streaming into the heliosphere. There is another characteristics of the hydrogen that is worth mentioning before we go into the pickup ions, that the hydrogen can charge exchange with an ion. And the reason is that the collisions, this medium is very collisionless, but the charge exchange is a dominant process that in hydrogen can lose an electron, become an ion, and an ion can capture that electron and become an hydrogen. This process happened right before the hydrogen come into the heliosphere. The ions slow down because they have to be deflected around the heliosphere. And by them slowing down, it increases the amount of charge exchange. And there is a pile up of the hydrogen, what we call hydrogen wall. So I'm not going to talk a lot about it, but just so you know that around the heliosphere, there is a pile up of hydrogen neutrals. And it's not part of this talk, but or part of these two classes, but a way that we were able to detect other astrospheres was by looking through these hydrogen walls around other stars. So we were able to observe that and see that the hydrogen wall exists. Okay, so what are the pickup ions? An ion come and a neutral encounter a neutral from the interstellar medium, and they can charge exchange, this process that I told you about. By them charge exchange, the ion that now has the characteristics of the original neutral from the interstellar medium is come with a very small speed, 25 kilometers per second. And this, what happened with this ion, another way that this can happen that is not shown here, the neutrals, when they come streaming into the heliosphere, they can be photoionized near the sun, really close to the sun, and also become an ion. So not just by charge exchange, but also by photoionization, and they become an ion with 25 kilometers per second. For the solar wind that is moving with a 400 kilometers per second, this is almost an ion at rest. So what ended up happening, that is shown in this diagram, the solar wind is coming from the sun, and the ion that was the original neutral hydrogen start gyrating around the magnetic field of the solar wind. And it ends up getting an electric field, the V cross B, due to the fact that it has in the frame of reference of the solar wind, it has a negative velocity of minus 400 kilometers per second. So it has a very intense electric field, just motional, V cross B. The fact that it's at rest with respect to the 400 kilometers per second solar wind, and it's gain energy, or we call it, the ion is being picked up. So very, very quickly after the neutral hydrogen get ionized, either by charge exchange or photoionization, it gets picked up near the sun and become part of the solar wind. And the energy that these pickup ions gain is around twice the energy of the solar wind, okay? And this process happens throughout. The solar wind come out from the sun and start moving to larger and larger distances and get what we call loaded by neutrals. It's gain more and more pickup ions. Where is the boundary of the heliopause? This is just to remind you, you probably saw it in Intro to Space Physics. If you do the pressure balance between the local interstellar medium and the wind, the ramp pressure of the solar wind, the magnetic pressure of the solar wind, and the pressure from the particles, you can figure out more or less where the heliopause is. Okay, how are we studying the characteristics of this very complicated interaction? With this type of missions, mainly from in situ measurements from Voyagers. We have two spacecraft, Voyager 1 and 2, that were launched in the 70s. They're still taking measurements. We also have IBEX and Cassini. Cassini is not working anymore, but for many years took, both with IBEX, maps of energetic neutral atoms of this interaction. The energetic neutral atoms are coming from when you create here in the heliosheaths. Now it's coming the heliosheaths. When you have a solar wind that has pickup ions and you charge exchange with a neutron from the ISM, the very energetic solar wind, the pickup ions, can create now a very energetic neutral called energetic neutral atom. Those neutrals will have an energy around 1 keV, and I'll come back to it in a bit. And they are the measurement that IBEX take. So they are looking at maps of 1 keV neutral hydrogen. They can only be formed by the pickup ions in the heliosheath that become neutral. Okay. There is also measurement by New Horizons that is now measuring the solar wind at very large distances. One interesting fact that I should mention right away, that neither Voyager and of course IBEX and Cassini take remote observations, has a working instrument that can measure pickup ions. The only instrument that can measure pickup ions is a New Horizons. So we will talk more about it later on. Voyager 1 and 2 were launched in '77. They're more than 40 years old. They are at, this slide is a little old, so they're beyond 140 and 115. And we do receive 8 to 12 hours of data from them. They're still working. Both of them are now beyond the heliosphere in the interstellar medium taking data. So we are right now looking with the Voyagers, and I will come back in the second part of this talk. Voyager 1 is here, Voyager 2 is in the south. So there are 2 points piercing this bubble. There are also Voyager 1 very close to the axis that we are moving, but 30 degrees away from it. And Voyager 2 is 30 degrees away from it and in the south. So it's 2 points in the 3D sphere, and both of them are now in this region of the interstellar medium that what we call mediated, influenced by the heliosphere. Anybody has any question before I continue? Okay.
I do.
Yes, Prasad?
Yes.
Yes, please.
I don't know if you explained this, but why is the extent of the termination shock different in north and the south? You are going to explain that?
There is so much to cover, but I'm hoping I will get to it. But I will just tell you quickly the answer for that. We discovered that back in 2006. This was before the crossing. We had a prediction, and then the crossing, this really confirmed it, that the heliosphere, there was no reason for the heliosphere to be symmetric north and south if the interstellar medium had some degree of asymmetry. So imagine you have an interstellar medium that is inclined here. It's going to exert a much stronger pressure in the south than the north by piling up of the magnetic field. So it's almost like you're punching a heliosphere this is going to be brought much closer to the sun. And this is one of the indications that we think that the magnetic field outside the heliosphere is highly inclined. Okay?
Okay.
Dinesh has another question. Oh, sorry, Prasad, you had another question?
No, that's all. Thank you.
Okay. So Dinesh has another question. It's a similar action in the heliotail. You know, in the last couple of years, this is the only thing I wake up and think is about the physics of the heliotail. It's a fascinating region, very little explored in the heliosphere because all the data came from the nose, from the Voyager, so we focus on the nose, and we left a little bit unexplored the tail. We do think that the heliotail, at least what I will tell you in part 2, that I think the heliotail has these 2 lobes embedded in a long plasma sheath, if you want. And those jets here are influenced by the magnetic field as well. So they're not symmetric, north and south. So they have the same type of reaction as the termination shock is pushed in. Probably the tail has a very different configuration as well due to the direction of the magnetic field. Okay.
Merav, about 10 minutes before the first break. Does that work?
Okay. That's perfect. I just got 10% of my slides, but it's fine. I knew it was going to happen. Okay. So Interstellar, the IBEX is a mission that measures the neutral hydrogen, and they are measuring most of the high precision measurements come from 0.4 to 6 keV. Those are neutral hydrogen. So imagine an X-ray, you're doing a tomography of the heliosphere. The plasma that has this energy to produce neutral hydrogen is a plasma that comes from the Heliosheath. So it has to be a plasma that is beyond the termination shock and is here, producing that type of energy. Cassini on board of Inca produced a neutral hydrogen with a much higher energy, 5 to 555 keV. What is interesting with the energetic neutral atom maps, something that Voyagers don't have in their measurements. Voyagers were 2 spacecraft that pierced the bubble both in the north and the south. And of course, the solar wind vary its characteristics with time, right? But when we get the data from Voyager, we have to try to separate the spatial differences from the temporal differences. What IBEX is able to do is to take maps of those energetic neutral atoms in different years. It takes almost a year to produce a whole map, 6 months to do the whole scan, but year to accumulate enough statistics. And what IBEX is doing since 2009 is taking maps, and here are maps separated by 2 years that show, this is organized in a funny way, I will come back to it later, but you can see the intensity of these maps, vary from 2009 to 2014. There is some variation, there is flickering in the sky, the intensity of the neutral atoms vary quite a lot. Both you can see by, look at the intensity here, 60, 140, 400. So the solar wind, this is what we believe is the influence of the solar wind vary in time that create different amount of neutral hydrogen in the sky. Okay, I have a question from Cole. Maybe this was already discussed, but this is mostly new to me. Why is there this directionality for the heliosheaths? Okay, so let me just go back here. So the heliosphere is organized through the motion that we are moving through the interstellar medium. So the motion of the interstellar medium is this one that my cursor is pointing, okay? And that motion creates the heliosphere being much thinner in the nose than in the tail. That motion is not in the galactic plane, in the direction of the galactic center. It's around 60 degrees from it, okay? Cool. Okay, now that we talk about the heliosphere, I know we don't have a lot of, how many more minutes? We have 8 minutes, Nick? Something like that.
Something like that, yes.
Okay, I'm going to try to do a touch and go really quick because I want to get to the juicy part of the heliosphere in the next class. Just some ingredients to remind you. If you want me to slow down, I'm happy to. But I just want to remind you that the sun vary, as you all know, in the solar cycle. The solar wind was discovered by Eugene Parker. And as you saw in the lab, the solar wind has a fast and a slow characteristics, both in speed, density, the level of turbulence. And this is a class, I'm not going to go through all the details. Why I'm mentioning it? Because that solar wind is the one that is going to impinge in the heliosphere. When you study the whole structure of our cocoon, you have to remember that what drives this is the sun and the solar wind. And because the solar wind vary tremendously in time, and the magnetic field vary tremendously in time, our cocoon is very complex because of it. And just again, I need to remind you on something that you might not have thought about it, but I need to go back to this slide to show you the sizes of this cocoon. It takes a year for the solar wind to come. Let me go from here. Take a year from the solar wind at 400 kilometers per second to come from the sun to the termination shock. Once the solar wind goes for shock, the solar wind is slower. Let's say 40 kilometers per second. Put 40 kilometers per second for the scales that we have here. This is a scale of, let's say, 400 AU. It take, or 200 AU, what you want, it take 400 years to take a wind that comes from the nose to go to 400 AU down the tail. By the time that that parcel of plasma comes from here and go down the tail, the sun changed many cycles. The sun has 11 years solar cycle. So the plasma in the heliosheath is an archaeology, is a solar wind that look back in time of what the sun was. And I know that this call is a long-term time map snapshot of the solar system. The heliosphere is your best archaeology to look back in time. The heliosheath plasma is not an instantaneous plasma. It's a plasma that is being enriched and slowly moving a very slow river through immense distances. So the solar wind here is going to change within a year, but it's going to take many decades for this parcel of plasma to go down the tail. Okay, so this is just to remind you that the sun changed and the magnetic field change. This whole parcel of magnetized plasma has to be carried down the tail. This is a slide I usually show how Parker discovered the solar wind and has a prediction that the solar wind is 400 kilometers per second. And Mariner with Marcia Neugebauer measured it for the first time. So we know stars, like the sun, has winds. So it's again mean that stars have astrospheres. Okay, now I know that a lot of you guys don't think about magnetic field at large distances. So I wanted to show you those slides to remind you how the magnetic field gets carried to large distances. The magnetic field near the sun has a lot of closed up structures and loops. But at some distance from the sun, you all know that the magnetic field gets stretched out. It's a stretched dipole and it's pointing mostly radially. So you can go through the derivation of it, and I'm not going to. I'm going to skip how you derive. You go from a closed loop, you put a wind, and Parker derived it that this is an expression of the magnetic field that come from a dipole being stretched by a wind. So you can go from first principles and derive it, and you have a radial component that fall with 1/r², and another component that fall 1/r², but there is an R here. So at large distances, the magnetic field from the sun is not 1/r², is mostly just an azimuthal component. Because you can think about a radial field that is getting steered up more and more by the rotation of the sun. Why it's important? Because I want you to have this mental picture. The magnetic field at large distances is a loop, is azimuthal. It's like a tornado. It's like that. And so if you look at the magnetic field, the red has this very twisted field up to the north, and it's changed polarity to the blue in the south. And of course, it's a much more complicated structure with a magnetic field. But one of the questions that we want to try to answer is how a structure like that is azimuthal and wound up, get carried to large distance from the sun. Nick, how much time I have?
We're right on top of the break, so if there's a story you want to finish up before that, that's fine.
Okay, so there is one little story, and then we can switch for the next class for the measurements. One of the critical questions that we want to answer is how the magnetic field gets carried into the large distances from the sun. And you all are familiar with the heliospheric current sheet or the ballerina skirt. And one question that I'm not going to go, I'm going to skip that, but I just want you guys to remember that. And if we have time in the second part, we can come back to it. There is a very interesting question, is an interesting plasma question, how a heliospheric current sheet that separates the magnetic field of the sun get carried to the end of the heliosphere. And we have measurements for Voyager past the termination shock that measure the polarity of the magnetic field. And these angles show that the Voyager was embedded within the ballerina skirt. So it seems that the ballerina skirt extends all the way to the edge of the heliosphere. So I'm going to stop here. I think it's a good point to have a break.
Yep, that seems like a good breaking point. So if there are any quick questions for Merav, that's great. And if not, let's take 10 minutes and be back at 20 after the hour.
Okay, great.
I have another question.
Yes.
You said that the particles, solar wind particles, move at 400 kilometers inside the termination shock, but when they get out, they move at around 40 kilometers per second.
Right.
So between the nose and the heliopause, a lot of particles should get bunched up, and there should be like a severe density contrast.
No, what happened with the speed, as a shock, the density goes up. The velocity goes down by this, and the density will go up by the same factor. So if you have a strong shock, let's say a compression ratio of 4, the velocity goes down by a factor of 4, and the density go up by a factor of 4 to conserve mass across the shock.
Yeah.
In fact, the termination shock was not a strong shock, it was a weak shock, but this is a different question. Okay, good. Okay, so I will be back in 6 minutes.
Feel free to turn your cameras back on. Oh, thank you. Feel free to turn your cameras back on. And just Catherine put a note in chat. Merav can't join us for office hours today, but she will. We have a time slotted in for next week.
Yes, I think it's a Wednesday.
Yeah.
Right. So write down your questions.
You can prepare your questions and really grill her on Wednesday.
Yeah, it's not a good idea, but anyway. I would be happy to. And if you can turn on the camera, that is great. I like seeing faces of people even at Zoom. I was going to mention something. I'm okay that I'm not going to cover all the material I wanted to, because I'd rather you guys just ask a question, understand what I'm trying to cover, than to, give you like, hose you with more and more information. So I'm happy to go slower. Okay. And finally, I forgot what usually I do. I show my real office so you can see the mess that it is, that you can turn on your camera. Don't feel shy that your house is a mess. Just look at mine. Okay. I'm going to share again and go directly to part 2. I just copy and paste one of the slides I didn't end up entering in part 1. Part 1 was more of an introduction. I have to say that one of the beauties of this area of research that still fascinates me is the richness of the plasma phenomena that is there. So I'm going to mention lots of plasma phenomena and ideas. Not all of them are going to go into depth. If you want to ask me more questions, I'm happy to try to answer. Okay, one topic to mention. I'm going to skip the solar wind at large distances in this part of the talk of the class. Just know that the pickup ions end up slowing the solar wind and ended up heating the solar wind. So there is interesting characteristics. Some of them I'm going to mention later. But the solar wind is what we call mediated by the pickup ions, the presence of the pickup ions. And I'll come back to it in a bit. What interesting thing, this was around the time when I entered this field. I entered the field in 2001. 2002, we started seeing data like that. This is the data from ions on Voyager 1. And Voyager 1 started, actually this is, Voyager 1. We started seeing particles coming with very interesting spikes in energy. And then a couple of years before we crossed the termination shock. And you all know by plasma books, you open and you know how you can recognize a shock. You say very fast flow, slow down. The shock usually, it's a very infinitesimal in time, in space, because it's controlled by the kinetic physics. So you have a very thin shock. And then you go to the other regime where the solar wind is slow and dense, like we talked before the break. But however, these contradict that somewhat. You have in regions of Voyager go 3 AU a year. So there is a pretty broad, almost 5 to 10 AU before the shock. So it's a macro scale phenomena where particles are escaping from the shock. You see something happen at high energy that come from the shock. And when you put this together, I was one of the people that tried to understand this data. We predicted that the termination shock has to be oblique to the direction of Voyager, and it has to be influenced by the interstellar magnetic field. So a couple of decades of AUs before we crossed the heliopause, there was a prediction that the heliosphere has to be asymmetric. Okay, and actually this asymmetry was proven to be correct. Voyager 2 crossed the termination shock at a distance much closer to the sun by 10 AU. Even when you include motions of these regions due to the fact that the solar wind change in time, you cannot account for that asymmetry. So you say it has to be some external factor pushing the heliosphere. And here is the data to show that we had a 400 kilometers per second wind that slowed down and then boom, went to a shock, a very weak shock. and we will come back to it. If you know shock physics, and Amitava has a great book about the chapter of shocks that I use a lot. Shocks can go up to, for an adiabatic shock, a strength of 4. This was a shock around 2 and a little even weaker than 2, where the speed went to 400 to here is 200 and slowed down to remain at 100. And the density, as we talk, increased by the same amount, okay? So it's one, the inverse of the other. The temperature of the solar wind went from 10 to the 4 to 10 to the 5. Let me just mention one thing about this temperature of 10 to the 4. If you take a solar wind from the sun and you adiabatically expand it to the end of the heliosphere, the temperature should fall much quicker. The temperature should not be as hot as 10 to the 4 Kelvin. The fact that the solar wind is hot as 10 to the 4 Kelvin means that something is heating up the solar wind. We think that the pickup ions are the ones that are doing that the pickup ions generate turbulence that are able to heat up the solar wind and continue heating by turbulence. So here comes again the non-ideal MHD phenomena, turbulence that can start in a fluid NMHD, but cascade to kinetic scales and heat up the solar wind. So this is an interesting phenomenon. Okay. The important part of this crossing was a new paradigm. When you look at the data of Voyager, this was published in Nature in 2005, and the speed, as I said, went down by not by a strong factor, but the density went up. When you use your usual Rankine-Hugoniot conditions of conservation of energy and mass flux through a shock, the solar wind that has a certain density and a speed of 400 kilometers per second needs to be converted into heat. And when you put the numbers, you should have a temperature on the order of 10 to the 6 Kelvin. But the temperature measured was 10 to the 5, an order of magnitude colder. And when we went back to think about it, where the energy went, there was a problem of energy, people realized that this is a shock, what we call mediated by pickup ions. So this is an interesting plasma problem. When the pickup ions are formed from the streaming of the neutral hydrogen, get photoionized and carried with the solar wind, you have two components in the solar wind, a cold that come from the sun and a hot, that those are the pickup ions that originally come from the galaxy. And because there's not a lot of collisions and not a lot of turbulence, those two components stays close to each other like two dyes. You can think about a red and a blue dye moving outwards without mixing together. So they contain their own temperatures, a cold and a hot. And you think about this, an interesting plasma problem when you have a shock mediated by two types of particles. Very massive cold, not very massive pickup ions, but hot. And you can explain that 80% of the energy will go through a shock like this to the pickup ions. The problem that we have, and Elena Povornikova will have a class for you guys about the interstellar probe, we don't have an instrument on Voyager that can measure pickup ions. So we imagine that this energy went to the pickup ions. We never measured it. And I wanted to jump from the basics, that was class 1, to give you a little bit of flavor of what the communities that study heliosphere are debating nowadays. So I'm going to skip a big jump. But one of the big debate is related with a lot of key observations that we see from Voyagers, from IBEX and Cassini that are not explained by our understanding and our theory and our models. And one of the key measurements that I won't talk in this class, but I just want to show you. This is the magnetic field, sorry, measured by Voyager those are the flows measured on Voyager 2. Voyager 2 has a plasma instrument. Voyager 1 does not have a plasma instrument. So they have to derive this speed from particles. And they use something called Compton gating. It's a complicated inverse technique to derive these flows. If this technique is correct, what in the last year we're trying to think that we're debating it, maybe it's not correct, but we thought it was correct. The speed of Voyager 1 was much lower in the Heliosheath. This is a snapshot of the Heliosheath from the termination shock to the Heliopause. The speed on the board of Voyager 2 was constant at 100 kilometers per second. And Voyager 1 dropped. This is just a radial component. I have to say that even the one that we measure on the plasma instrument, it's a bit puzzling. Because think about a flow that goes against a wall with the Heliopause. It has to be slowly deflecting. The speed should be going down, the radial component, because you're slowly going to the sides. But the speed on Voyager 2 was flat. And Voyager 1 did go down. If you put a MHD model to try to reproduce these flows, the models cannot reproduce these flows. So it tells us that something we don't understand about the flows in the Heliosheath. Maybe the more exciting puzzle that we have is the crossing of the pickup ions that I mentioned through the termination shock. Why it's important? Termination shock is the largest shock in the heliosphere. So you guys probably learn about shocks near the sun or in the interplanetary space. The largest shock in the solar system is a termination shock. So you think that you should be able to predict how particles go through shocks, right? So if you look at the pickup ions that are energetic particles, they should be able to go through the termination shock and get somewhat accelerated because shocks accelerate particles. So the prediction of an acceleration of particles from a shock, forget the labels here, but you can think about intensity versus energy. And in this regime are the cold solar wind. This regime are the hot pickup ions, and then you go to the galactic cosmic rays. And the prediction was that before the shock, you will have a spectrum like that. This is measurements. And after the shock, the solar wind is going to be heated by a little bit and accelerated by a little bit. So it should go this way, this dashed line. And the pickup ions should have been accelerated. And the prediction was that the pickup ion will come, we start getting accelerated to what we call anomalous cosmic rays. Those are particles around MeV. So you take a 1 keV particle and you bring it up to MeV. And you can see that the observations shown in red don't match the dashed lines at all. So if you look at the intensity of particles before and after the termination shock, the particles didn't notice that there was a shock. So this is a major, major puzzle in the heliosphere. It's also called in question, do we really understand acceleration of particles or not? And it's come to one of the questions that I don't remember who asked me about if the termination shock, why the termination shock of Heliopause was not wiggled, why the bow shock was wiggled in that cartoon. One of the explanations of why we didn't see the acceleration of particles is because, in fact, the termination shock is wiggled, and somehow Voyager has the bad luck to go in a region when particles were not accelerated due to the wiggles, due to the turbulence. I am a little skeptical about this theory because Voyager 2 also crossed the termination shock and also didn't see acceleration. You have to remember that the shock is weak. So it's not a very good shock to accelerate particles. But it's an interesting universal question on the acceleration of particles. Okay, the other piece of the information, that the particles that you expected to be accelerated, those are ions that are in energies of MeV, very energetic, keep increasing. So if you look at the intensity of these particles as the spacecraft went in the heliosheath, look at the red curve, their intensity increased. So they didn't increase across the shock, but they increased ahead of the spacecraft. It tells us that there is a mechanism of acceleration somewhere else in the sheath, not in the location of the termination shock. So I think those two questions are very exciting because it has a very broad implication for acceleration of particles in general in space physics and in astrophysics in general. Okay, the other problem we are debating within the community, besides the shape that I'm going to come to it in a minute, is the thickness of the sheath. As I said, when Voyager crossed the Heliopause, the thickness turned out to be 28 AU at Voyager 1 and 35 AU. It's very thin compared to what models predict, that is around 50 to 70 AU. So something is thinning the sheath. And there is lots of ideas. Maybe we forgot to include conductivity in our models. Maybe we forgot to include reconnection. There is something that is extracting energy from this sheath. And in a maybe again bigger way to think about it, non-ideal effects are playing a dominant role in the heliosheath, and we can measure it. Anybody else? Yes,
there's a question from Cole. And the question is, maybe this was already discussed, but this is mostly new to me. Why is there directionality for the heliosheath? Where is the bow shock?
Amitabha, I did answer it in the first class.
Okay.
Yeah, but I do have another question about this. Actually.
Go for it. Go for it. I love questions.
As chance would have it. So this 28 and 35 AU for Voyager 1 and Voyager 2.
Yeah.
Are those I don't know how to phrase, consistent with one another? So is it expected that that point was actually different just at the different places that Voyager 1 and 2 interacted with the heliosheath, or is there some errors associated with that?
I don't know if I understood your question.
Okay, my question is that difference just due to the heliosheath extending farther out for Voyager 2 than Voyager 1? Or,
it's a complicated answer on that call. I think you can, I think this will be consistent with the heliosheath being the same thickness. If you include time dependent, time dependent can account for 7 AU of differences.
Really? Okay. Okay.
Yeah.
Yeah. Okay.
So it's almost consistent. It's a little puzzling. I would have expected the sheath to be thinner at Voyager 2. But there are time dependents that could account. But what they cannot account is to bring from 70 AU to 35, a factor of 2. Okay. This is, you can't. Time dependent, maximum, at least what we think, 7 AU of a motion, but maximum that you can push it.
Great, thank you.
Okay. The other question that we are debating as a community is about the last boundary. So now I left the termination shock. I went through some puzzles in the heliosheath, and now let's go to the heliopause. And a question that I like to phrase it is, we live in a house. This is our cocoon, our heliosphere. And you would think that we know how thick the walls of our cocoon are, or how porous the heliopause is. The properties of our external wall are not well understood. And I'm sure, and I have a lot of slides about it later on. I'm not sure if I will get to it, but I will show you here 2 different crossing of the heliopause. This is Voyager 1, and this is Voyager 2. And, and those are galactic cosmic rays in the top panel, and the lower panel are energetic particles from the sun. So those are energetic particles in a much higher energy than the bulk solar wind that is a 10 to the 4 Kelvin or 1 keV in pickup ions. Those are 50 keV to MeV. So those are, you can think about individual particles, test particles. And those are different intensities measured at Voyager 1 in time. Voyager 1 in the September of 2012 starts seeing some dips in the intensity in all energies. And then it came back to the same level as before. And a couple of months later, another dip in all channels. And by the end of 2000 and here 2012 and 6.5, so middle of the year, the particles on 50 keV disappeared. The particles at 100 disappeared. 500 keV disappeared, and MeV remained a small tail until they completely were gone. At the same time, and it's exactly the same time, the galactic cosmic rays started increasing abruptly, then decreasing again, increasing abruptly, then decreasing again. And you can line these stories up by mid of 2012. All the solar wind particles disappeared, and the galactic cosmic rays intensity were way up and constant. The interpretation that people had is that we crossed the Heliopause because suddenly the solar wind particles disappeared and the galactic cosmic rays were high. I will come back to it later, but the magnetic field, remember that we thought the magnetic field has to push the southern hemisphere? You expect it to be highly inclined. And the magnetic field measured during this crossing was not highly inclined. So there is a puzzle here. But at least you can see that in these episodes here, the heliopause was porous. Particles came into the heliosphere before we crossed the heliopause. The Voyager 2 crossing was very different. Voyager 2 crossing, is shown here on the right. And we are trying to figure out where the heliopause is. But in day 310 of 2018, the particles of the galactic cosmic ray start going up until they plateau here. At the same time, the solar wind particles started decreasing, but this decrease lasted quite a lot. And there was no episodes of porosity. The particles came in before. I worked with some colleagues of mine to try to explain this data as fact that the porosity appeared because there was some nearby reconnection sites that let magnetic field and particles come into the heliosphere before the heliopause. But you do need to understand then why on Voyager 2 this did not happen. Why the connection is suppressed there. Okay. So the other question that I want to discuss is how the heliosphere look like. And before I go there, the properties of the pickup ions that I said that are so important, we would like to understand them. And I'm not going to talk in this class about it, but we need to understand how they become a pickup ion, a cradle, and how they evolve from becoming a pickup ion near the sun until they charge exchange and they become neutrals or they're graved, they disappear and they leave. Once they become in a neutral hydrogen, they can stream and leave the heliosphere. One of the big problems that we have that Voyager is blind to pickup ions. It cannot measure pickup ions. So when you look at the distribution of particles, this is the thermal distribution, the solar wind, the code. This is energetic particles that we do measure in Voyager, but this middle piece that we need to understand, we are not measuring. So Elena Povonikova will give you a class about the interstellar probe. We need to have an interstellar probe go out there and measure these particles to really understand this system. Okay.
Hey, Merav,
Yes.
we've got one question. Brian, I'm not sure which graph you were referring to. Is this the high energy graphs, the GCR?
No, I think it's this one here, right? The dips. Brian, is this
Yes.
dips could be related to the structure compressing and expanding? That is, again, a very interesting question. Okay, so when you look at data on Voyager or this in situ data, there is always a question if this is something spatial or temporal. And it could be that what happened, we were in and out from the heliopause. Somehow the solar wind compressed or compressed or expanded, and the termination shock in the heliopause and the whole system compressed or decompressed. I am on, so it's possible, Brian. I want to rule it out. There are people that think that it has to do with the temporal. I think when you try to put a temporal picture, it doesn't match so well with the story. I think the spatial explanation is a much better one, but I'm not going to rule out the temporal. It's possible.
Thank you.
Okay, anybody has another question? Okay, so one thing I just wanted to mention that when we are trying to understand.
Merav, I'm so sorry.
No, go
I'm
ahead.
lagging behind because I'm trying to read up this. Brian is asking a question. Is there any way to know if this?
No, he just asked and I answered, Amitabh.
I'm so sorry, my fault.
No, it's good because before you gave a chance to call to ask another question. So maybe Brian has another question. No, okay, so we go ahead. I wanted to mention the fact that we're trying to understand the pickup ions and how they evolve. And I talked about the heliosheath being thin. It also means that there might be effects that we're not including in the global models. And some of them can be related to reconnection, turbulence, or acceleration of particles. So here is a snapshot of a hybrid code from Giorgio Coloni that look at how turbulence from the supersonic solar wind, shown in blue, get transmitted through a shock. And this is answering the question that one of you guys asked about the ripples in the shock. Turbulence can ripple the shock and can change the conditions of the shock. So it's possible that acceleration of particles or pickup ions were affected if Voyager 1 crossed in a dip, in a place where particles were not accelerated. But then you want to understand how this acceleration and compressions affect the pickup ions in the sheath. Same thing with reconnection. And I had several works looking into effects of reconnection. We think it might have an important effect. Okay. Finally, there is a bigger question too that the community is trying to understand is how far upstream the heliopause we affect the interstellar medium. So, you know, when I entered the field 20 years ago, we thought that once you cross the heliopause, you have a very quiet interstellar medium. And I am showing you now a graph, a compositive graph of the data measured in the local interstellar medium. And so this is the crossing of Voyager 1 in 2012 into the interstellar medium. And the galactic cosmic rays, went way up and stayed flat. The particles from the sun, the anomalous cosmic rays, flat. They went down and plateau. However, if you decompose the galactic cosmic rays in directions and you look in more details how the galactic cosmic rays behave if they are parallel or perpendicular to the magnetic field, there are some dips. It means that something weird is happening. The galactic cosmic is outside the heliopause that we don't understand. It means that the heliosphere is affecting the magnetic field outside. And we, again, don't understand. Is it shocks, for example, driven from the sun that make their way all the way into the interstellar medium, or there's something else? So in a bigger question, we would like to be able to understand how far the heliosphere influence extend into the interstellar medium. The other interesting piece, we do measure explosions that come from the sun, like coronal mass ejection, that build up compression in the interstellar medium, and they produce radio emissions. Those radio emissions are detected on Voyager, and are shown here in these red peaks. So this seems an indication that there were shocks in the interstellar medium. And this is a graph that ends in 2016, but this can be extended to 2021. Voyager continue to see perturbations and influence from the sun into the interstellar medium. We haven't gone to a region where the interstellar medium is quiet. So it's something, again, that puts us in a bigger question, how far influences of stars extend into the medium that surround them. And there is very interesting plasma physics that I'm not going to go into it, is how these shocks are altered in the interstellar medium. It's a different plasma. Okay, let me skip this and come back at the end of the class about this issue. This is a very interesting question. Let me talk about a question that I'm running a NASA center called SHIELD. You are welcome to just Google SHIELD, NASA or Merav, and you will get to the webpage of SHIELD. Or Nick can put the webpage if he wants. This is one of the questions that we're trying to answer within the center, is what is the shape of the heliosphere? And again, it's, I think, a little embarrassing for the community that we don't understand even the very basic shape of the heliosphere. So the typical idea that the sun moves through the interstellar medium, and you have this long comet shape that extends to thousands of years. But now we are trying to debate that, starting to debate, maybe it's a sphere, maybe it's a cool sun. So why is this debate? Why does this debate happen? It's come back to classic work by Eugene Parker, the same guy that discovered the solar wind. When Parker was thinking about the shape of the heliosphere, he ignored the solar magnetic field and thought about, if the sun has a wind and it's moving through the galaxy, you will have a comet shape like that. However, if by the time that the sun has a wind, moves through the galaxy, and you include a very strong interstellar magnetic field, the plasma outside of the heliosphere is going to be organized by the magnetic tension of the interstellar magnetic field. So you might have, you can solve the equations, you can look in Eugene Parker original work 61, and you can get a tube-like heliosphere, not a comet shape. So it's Parker realized at that time that the shape of the heliosphere might be dependent of the external forces. One thing to remember, Parker ignored the influence of the solar magnetic field in this work. I have a question by Dinesh. How much influence? Dinesh, this is something that Dinesh is asking how much influence the interstellar medium has on the heliosphere. This is a question that we're debating. It's come back to the strength of the interstellar magnetic field that we don't know. We do see that the termination shock on Voyager 2 was much closer to the sun than Voyager 1. So there is some influence there. But now we are debating about the Heliopause. Okay. So the working paradigm is, as I said, the comet shape. And this came also from simulations that ignored solar magnetic field that showed a comet shape. This came from the Moscow group led by Vladimir Baranov back in the 90s. They did the first simulation of the heliosphere. Now let's go back to the energetic neutral atoms and the maps that I described to you. The IBEX Voyagers 1 went through the nose, right? And IBEX ENAs were the first time when we look back to the tail. Some of you guys asked about the physics of the tail. So IBEX in 2003 took the first maps of the tail. It's a question from Cole. This reminds me of the comparison between high and low Reynolds numbers flows. It's only different with dependence of the you mean, Cole, about
Yeah, I think he means this slide, Merav.
this slide, Cole?
Yeah, I think
Right.
so.
Yes.
So here you are assuming zero viscosity, even in ideal MHD.
Right.
If you have a very strong magnetic field outside. So forget viscosity here.
Okay.
So you have zero viscosity if you have a very strong magnetic field. The tension of the field will drive the flow as the magnetic field wrap around the plasma outside is going to follow the curvature of the magnetic field. And the curvature of the magnetic field outside of the interstellar medium is going to force the heliosphere into this tube-like shape.
Okay.
If you include viscosity, then other effects can happen. Okay, but a good question. So coming back to my little story, that when IBEX looked at the heliospheric tail in ENA maps, remember that the ENA measure pickup ions from 1 keV to 5 keV in IBEX, the maps, so now we are looking down the tail. This is downwind. I'm here in the sun looking downwind. The maps look from 0.7 keV to 5 keV like that, very different. Like somebody's turning on the lights in different locations, right? And Dave McComas and their team explained that due to the fast and slow wind coming down the tail, the main difference. Because the paradigm was we have a long tail, right? Okay, great. What happened with the Cassini ENA? The Inca ENAs measured the ENAs from 5 to 50 keV, much higher energy. And they look back at the tail and in all directions and notice that the intensity of the ENAs is similar. So they came up with a paper that was published in Nature Astronomy in 2007, arguing that the heliosphere has to be bubble-like. Because if you had a tail-like, you will have much more energy coming, much more energetic neutral intensity coming from the tail, right? Now came my group to mess up things. We were focused on the solar magnetic field effects. One of the things I noticed, and I'm coming back to what we finished in, let me move my, yes, Catherine, you said 10 minutes left, right. I'm going to try to finish this story and open for questions. But the issue of the magnetic field in large distance from the sun. As we said in the last class, the magnetic field is mostly azimuthal, right? It's because of the large distances, the radial component fall to zero, while the azimuthal is spiraling up. The magnetic field of the sun in all these decades were ignored because the idea that the plasma beta, the ratio between the thermal pressure and the magnetic pressure is much larger than 1. So if you have a high plasma beta, just ignore the magnetic field. And what is interesting that when you think about it, the plasma beta is high, but the ratio between the RAM and the magnetic pressure it's not a plasma beta, is the ramp pressure over the magnetic pressure is around 1. So the magnetic pressure might be much, much less important than the thermal pressure, but it's on the order of the flows. So in this diagram, going to the wrong direction. In this diagram, when you have the solar wind going down the tail, trying to stretch these field lines, the magnetic field of the sun is going to resist the stretching and is going to start confining the plasma into 2 jets. It's going to stop not wanting to be stretched anymore and confine the flows to the north and south. So this discovery that we did actually came about in a fluke. When we were doing numerical simulation, I noticed it, and then I made in the back of the envelope, and I realized the magnetic field cannot be ignored because it's comparable to the flows. So what we discover, and other simulations in other groups agree with that the solar magnetic field has this very funny slinky geometry. So you think about the magnetic field near the sun being this radial. Now put some rotation of the sun, and if you forget everything I said this lecture, at least remember that the solar magnetic field at large distances is like a slinky. And because of the motion through the interstellar medium, the slinky is curved away from the motion that we have in the interstellar medium, okay? I have 7 more minutes. I just wanted to mention something else. Recently, we did another work that I wanted to bring back this idea of the pickup ions. The fact that the solar wind near the sun is not, or actually large distance from the sun, is not just one component, cold and massive. It has also a much more rarefied component, 25% in density, but much hotter in pickup ions. When you put them together, they don't mix very well because there's not a lot of collisions, but we did some simulations and we showed that these 2 jets remain. But because most of the energy go into pickup ions down the termination shock, the heliosphere looked very different. It looked much more spherical, much more deflated. So it's instead of doing this comet shape long, it's a sphere. It's much more in the direction of what Cassini and Nays are telling us. The reason for that is that the pickup ions carry all the energy. Here's the termination shock in black, but they can charge exchange again and leave the system. So they extract energy and deflate the heliosphere. So we ended up in the cover of Nature Astronomy just to show that not even the shape of the heliosphere we know, but we think it's this cross section of it. It's like a crescent or a croissant, I like. So it's thin in the nose and a little thicker towards the northern and southern, but toward the tail, it has not that of a difference of thickness than towards the nose. It's a little thicker, but it's not thousands of AU. And this is because the Heliosheath flow gets funneled by the solar magnetic field. So it's an interesting story that even that the solar magnetic field is not the dominant character in this physics, because the thermal is much more important. It's a dominant factor as a skeleton of the heliosphere. That is not something, when I go back to where Parker had the original figures of Parker, there was no solar magnetic field. So if you put a solar magnetic field, suddenly you split these 2 and you make it much smaller, much more like a crescent shape. And there will be a mission in NASA coming in the next couple of years that will climb up, look at this region. I think what I will do, since I only have 5 more minutes, is to skip to just last slides. I'm going to skip some of the physics. I wanted to go. First of all, to tell you, if you guys want to go, here's the shield again. We have a big component of shielding outreach. So I know a lot of you guys are young in your career. We have a happy hour there. We have a place when we have people that are not part of the center reaching out to record testimonials, how they got to be a space physicist. So I see a lot of your faces all over the world. If you want to participate, be part of this story, we will be super, super interested. So just email me or shieldoutreach@gmail. We're interested in collecting stories under this umbrella. You can't be what you can see. We're trying to inspire the next generation of students that will recognize themselves in this cohort. Okay, so I'll just leave this, my last slide. Voyagers have sufficient power until 2030, so they will keep taking pictures and data, and we still have IMAP that is going to take ENA pictures. I have some, and I wanted to open for question. I have some question from Rigo. The Heliosphere look like Kelvin Hamilton instabilities actually pinch and shut off. Rigo, this is a very, very good question. I have a paper now being reviewed where we are explaining these instabilities that you probably captured. I don't know which one you're talking, but this one's here.
Yes.
As generated by Rayleigh Taylor. Due to, again, the neutrons coming in and playing a role. And so if you email me, I can email you and point out, it's a very interesting physics that I didn't cover here.
Yes, I'd love to read the paper.
Yeah, please email me. We can talk offline or in office hours next week.
Great, thank you.
Great. Anybody has another question? I know we have 2 more minutes.
Merav, I'd like to thank you for a very nice lecture. Thank you so much.
Pleasure. I gave a lecture many, many years ago about shocks, and it's so much fun to come back.
It's getting better all the time.
This is a great school. I love this school.
Thank you.
Great effort that you and Dana are putting. Fantastic. Great, folks. So please think about questions. Come to my office hours on Wednesday. We have more time to debate specific questions or aspects I didn't cover. Great. Thank you, Nina.
Okay.
Great.
Thank you, Merav.
Bye, folks.